Ever get that feeling, like there just has to be a quicker way, not just through traffic, but maybe a real shortcut through time or space itself?
Hmm.
Well, that's where things get really interesting, where time travel and warp drives crash into, well, actual physics.
Yeah.
And that's what we're diving deep into today. We're going to explore this really mind bending stuff, pulling from the work of Alan Everett and Thomas Roman. We've seriously looked into this.
They really have.
Now, don't worry if your astrophysics is a bit rusty. The aim here isn't to, bury you in equations. It's more about pulling out the really fascinating ideas about crossing the cosmos faster than light, or maybe even, well, traveling through time.
Okay.
So, whether you're a science buff or just, like me, maybe watch a bit too much sci fi,
Yeah. Yeah.
our mission is to see how these things we usually see as separate warp drives, time machines, are actually like deeply connected in physics.
That's the surprising part, isn't it?
So, yeah, settle in. Your ideas about space and time might need a little adjustment.
That's absolutely right. What's really fascinating and often missed in sci-fi is exactly that connection. Faster than light travel and backward time travel, they're not really separate issues in the physics.
How so?
Well, the math you need to bend space-time, the kind of warping for a warp drive or a wormhole shortcut.
Yeah.
That same math often doesn't really care if it's making a shortcut through space or a loop in time.
Huh. Okay.
Yeah, a big moment for physicists really digging into this was back in '88, a paper by Morris, Thorne, and Yurtsever on wormholes and time machines.
Thorne. Kip Thorne, the relativity expert.
That's the one. His involvement really signaled, okay, maybe there are some loopholes in general relativity we should look at seriously. He's known for exploring those edges.
So right off the bat, warp drives and time machines are kind of two sides of the same coin.
In a very strange theoretical way, yes. That's a key takeaway. They're deeply intertwined in the physics.
Okay, let's unpack that strange coin. So Einstein's theory of gravity, general relativity, it hints at breaking the light barrier or even going backward in time. That sounds wild.
It does, doesn't it?
But maybe we should back up a bit. Like, talk about special relativity first. How does that fit in?
Absolutely. Good idea. Special relativity, which came first, is really the bedrock here. It tells us things get weird near light speed.
Right.
Time slows down, distances shrink.
Yeah, time dilation and all that.
Yes. And mathematically, within special relativity, going faster than light gets tangled up with moving backward in time. It's baked into the equation, the Lorentz transformations.
Okay.
Then general relativity builds on that.
Right.
It gives us space-time not as a fixed stage, but as this flexible fabric. Mass and energy warp it.
Like the cosmic trampoline analogy.
Precisely. And those warps, those curves and dips in the trampoline, that's where the potential for shortcuts and time loops comes from.
So those dips, that's where wormholes might fit in. I mean, you see them everywhere in sci-fi, Star Trek, Stargate. Are they actually like a real physics prediction?
They are, well, theoretically predicted anyway. General relativity's equations do allow for solutions that look like tunnels, shortcuts, connecting distant points in space-time.
So the sci-fi writers were onto something?
They were definitely inspired by a real physics concept, yeah.
Yeah.
Now, whether they could actually exist and, crucially, be stable and traversable, that's the huge question.
Right. You wouldn't want it to collapse on you halfway through.
Exactly. So theory allows them, but making and keeping one open, that's the major hurdle.
Okay, so wormholes are like folding space. Got it. But what about warp drives? Like in Star Trek, just engaging warp? That seems more direct, less about finding a tunnel. Any science there?
There are theoretical models, yeah. The Alcubierre drive is the most famous one. The idea isn't that the ship itself breaks light speed locally.
Oh. How does it work then?
It's subtler. You'd theoretically compress space-time in front of the ship and expand it behind. Creates a sort of bubble that carries the ship along, like surfing on a wave of space-time.
Surfing space-time.
Yeah. And there's another idea, the Krasnikov tube, which is more like a pre-built one-way hyperspace tunnel you'd have to construct first.
But But do these also connect back to time travel?
That's the expectation, yes.
Hmm.
Just like with wormholes, the kind of extreme space-time bending needed for these warp drives, according to the math, seems very likely to also allow for creating closed, time-like curves, time loops.
Wow. So hitting warp speed might accidentally let you visit yesterday.
Theoretically, could open that door. It seems like any time you mess with space-time enough to beat light speed, you risk enabling time travel too.
Okay, but that immediately brings up all those paradoxes, right? The grandfather paradox being the famous one. Go back, step on a bug, prevent your own birth. How does physics even try to deal with that?
Yeah, the grandfather paradox is the big headache. When physicists got serious about time travel math, paradoxes were a major focus. Two main ideas came up.
Which are
One is sort of nicknamed the banana peel mechanism.
banana peel.
Yeah. The idea is that the laws of physics themselves would somehow conspire to prevent a paradox. You try to eliminate grandpa, but you slip on a banana peel or your ray gun jams or something always stops you. Consistent history wins out.
So self-healing timeline, kind of?
In a way, the other idea is maybe even weirder. The many worlds interpretation of quantum mechanics from Hugh Everett, no relation to Alan Everett, by the way.
Many worlds, like parallel universes.
Essentially, yes. Every time there's a quantum choice, the universe splits. So if you go back and change things, you just create a new branch, a different parallel universe. Your original timeline remains untouched, so no paradox there.
Okay, banana peels or branching universes. Reality finds a way, it seems. Let's rewind a bit, pun intended. H.G. Wells' The Time Machine. What does that classic tell us about how we think about time?
Oh, Wells. It captures that deep human desire to move through time like we move through space, right? But it also bumps up against problems right away. Well, the idea of just jumping instantly between times. Where does the machine go during the jump? What about conservation of energy? Keimsikoet tells us mass and energy are linked. You can't just vanish and reappear without accounting for that energy.
Right, you can't just poof. Physics demands some accounting.
Exactly. So Wells nailed the desire, but the mechanism he imagined, that instant jump, seems pretty problematic based on physics.
Makes sense. And the book also stresses relative motion and frames of reference. Why are those so critical here?
They're absolutely fundamental. Nothing's truly stationary. Motion is always relative to something else, your frame of reference. And to compare events, you need synchronized clocks within that frame.
Okay, seems simple enough.
It seems simple, but Einstein showed it gets really weird near light speed. Our common sense way of adding velocities, Galilean transformations, just breaks down for light.
That was the Michelson-Morley experiment finding, wasn't it? Light speed is constant no matter how you're moving.
Precisely. A huge discovery. And from that constancy, Einstein built special relativity on two postulates.
Yeah.
Laws of physics are the same for all constant motion observers, and light speed in a vacuum is constant for everyone.
And those simple rules lead to?
They lead to the Lorentz transformations. These are the correct rules for relating space and time between moving frames. And they show time is an absolute. Moving clocks run slower, time dilation.
Time dilation, and that's been measured, right? It's not just theory.
Oh, yeah, absolutely.
Yeah.
Atomic clocks on planes, particle accelerator. It's real. The Lorentz math also gives us the light barrier.
How so?
As you approach light speed, a factor in the equations, a square root term, goes towards infinity. It means you need more and more energy to accelerate further. Infinite energy, actually, to reach light speed if you have mass.
And that connects to E, Missikawa.
Exactly. Energy has mass equivalents. As you add kinetic energy by going faster, your effective mass increases. That increasing mass makes it harder and harder to accelerate further, requiring infinite energy to hit C. It's the ultimate speed limit for matter.
Okay, so an unbreakable speed limit, time warping. Space-time is weird. How do we visualize this? The book mentions world lines and light cones.
Right. Think of space-time as this 4D map 3 space, one time. A world line is just the path an object takes through that map over time. Stationary object, straight line up the time axis. Moving object, angled line.
Okay. And light cones?
Imagine an event, a flash of light, say at one point on that map. The light cone spreads out from that event into the future and converges from the past. The cone's surface is the path of light itself.
So it defines what can affect what.
Precisely. Anything outside the future light cone is unreachable without faster than light travel. Anything outside the past light cone couldn't have influenced the event. Light cones map out the causal structure of spacetime.
Cause and effect, limited by light speed. Got it. What about the twin paradox? That one always twists my brain.
Ah, yes, the twins. Astrid stays home, Barnaby takes a fast spaceship trip, comes back younger.
Right. Yeah, but from Barnaby's view, wasn't Astrid the one moving? Why isn't she younger?
The key is asymmetry. Barnaby had to accelerate, blast off, turn around, slow down. Astrid didn't. She stayed in roughly one inertial frame. Barnaby didn't. That acceleration is what breaks the symmetry and makes Barnaby the one who ages less.
It's the acceleration, not just the speed.
Exactly. We talk about proper time, the time measured along a specific world line. Barnaby's world line involved acceleration, and the total proper time elapsed along it is less than Astrid's.
Okay, that helps unknot it a bit. Acceleration is the differentiator. Now, what about those hypothetical faster-than-light particles, tachyons? Are they just sci-fi?
Tachyons are purely theoretical. If they existed, they would always travel faster than light, and the math gets really weird.
How weird.
Well, according to special relativity, a tachyon moving forward faster than light could appear to an observer moving backward in time to have negative energy.
Negative energy
Yeah.
and backward time travel just from going faster than light.
According to the math, yeah. It's incredibly counterintuitive. And it opens up huge causality problems, like sending a message to your past self to prevent the message being sent. Classic paradoxes.
So how did physicists try to fix that?
There was the reinterpretation principle.
Yeah.
The idea was maybe what looks like a negative energy tachyon going backward in time is really a positive energy anti-tachyon going forward.
An anti-tachyon.
Yeah, the way to kind of flip the perspective.
Yeah.
But even with that, the potential for sending information back in time and causing paradoxes didn't really go away. It's still deeply problematic.
And didn't Alan Everett's work suggest you'd need something really strange, like a preferred direction in space, to make faster-than-light travel consistent without paradoxes?
Yes, that was some really interesting work. He and colleagues showed that if you try to build a consistent math for superluminal observers, you basically end up needing to break the isotropy of space, the idea that space is the same in all directions. You need a special preferred direction.
Which goes against everything we observe, right?
Pretty much. It's a radical idea.
Yeah. So where did the whole tachyon thing end up?
Mostly fizzled out by the 80s. It was a fascinating thought experiment, and it really helped clarify the link between superluminal travel and time paradoxes. But zero experimental evidence for them. And theoretically, they cause other problems too, like maybe making stable particles like protons decay when they shouldn't.
Okay, so no tachyons for our warp drive fuel. Got it. But they highlighted the time travel connection. Let's shift to time itself. Why does it only flow one way? Physics laws seem mostly time reversible, but our experience isn't.
That's the arrow of time problem, a huge mystery. At the micro level, run the equations for gravity or electromagnetism backward, and they still work fine. Like billiard balls colliding forward or reverse looks okay.
But not a broken glass reassembling itself.
Exactly. That looks totally wrong in reverse. The difference seems to be the second law of thermodynamics and entropy.
It's a measure of disorder.
Right. Closed systems tend towards more disorder over time, simply because there are vastly more ways to be disordered than ordered. A shattered glass is a much higher entropy state than a whole one.
So the arrow of time comes from entropy increasing.
That's the prevailing view. It's not that the fundamental laws themselves have a preferred time direction. Mostly, there are some subtle exceptions in particle physics. It's more about the universe's initial condition starting in a state of incredibly low entropy near the Big Bang.
Hmm.
As the universe expands and evolves, its entropy increases, and that overall increase gives us the perception of time flowing forward.
So we're just surfing the wave of increasing cosmic messiness.
Uh, that's one way to put it, yeah. It's a statistical effect emerging from the universe's starting point.
Mind bending. Okay, let's pivot to gravity. Newton saw it as a force. Einstein saw it as curved spacetime. How did that shift happen?
It was revolutionary. Einstein puzzled over the equivalence principle, why inertial mass, resistance to acceleration, always equals gravitational mass, how strongly gravity pulls.
His elevator thought experiment.
Exactly. Someone in a closed accelerating elevator in space can't tell if they're accelerating or just sitting still in a gravitational field on a planet. The effects are locally identical.
Simple but profound.
Very. He generalized this, realizing gravity wasn't a force acting instantly across distance, like Newton thought, that conflicted with light speed being a limit. Instead, he proposed that mass and energy warp space-time.
The cosmic trampoline again.
Right. And objects just follow the straightest paths possible geodesics through that curved space-time. Planets orbit not because they're pulled, but because they're following the curves made by the star's mass.
And this curvature is key for our discussion.
Absolutely. Because if space-time can be bent and warped, maybe we can bend it in extreme ways like wormholes or warp drives. General relativity predicted things like light bending near the sun, clocks ticking differently at different heights, all confirmed.
And extreme objects like black holes.
Yes, regions of incredibly intense curvature. Near a black hole's event horizon, the point of no return time dilation gets extreme. Time slows to a crawl for someone falling in relative to someone far away.
You mentioned surviving the fall into a big one.
Theoretically, yes, for a supermassive black hole. Tidal forces, the stretching effect of gravity, are actually weaker near the horizon of a very massive black hole compared to a small one. You'd cross the horizon intact, though doom awaits at the singularity inside.
Less immediately spaghettified, anyway. Okay, so GR gives us bendy space-time, but then there are designer space-times and energy conditions. What's that about?
Well, mathematically, you can design almost any space-time shape you want. Then Einstein's equations tell you what kind of matter and energy you'd need to create it.
But not all designs are physically possible.
Right. That's where energy conditions come in. They're like physics rules of thumb about what kinds of matter and energy are reasonable based on what we observe. The weak energy condition, for example, basically says energy density should always be positive or zero. No negative energy allowed.
Okay, reality checks on the math.
Exactly. And here's the rub. Things like stable traversable wormholes or Alcubierre warp drives seem to require violations of these conditions. They need exotic matter with negative energy density or negative mass.
Exotic matter. Is that like antimatter? Star Trek uses that.
Good question. Common confusion.
Yeah.
No, it's totally different. Antimatter annihilates with matter, releasing lots of positive energy. This theoretical exotic matter would have truly weird properties, like negative mass, push it, and it accelerates towards you, or gravitational repulsion.
Wow. Okay, that's seriously weird stuff. And we need that for wormholes and warp drives.
That seems to be the requirement according to GR in these energy conditions. The huge problem is we have zero proof that macroscopic amounts of this stuff exist.
But maybe tiny hints from quantum mechanics, like the Casimir effect or Hawking radiation?
Exactly. The quantum vacuum isn't empty. It's full of virtual particles popping in and out. This can lead to tiny, measurable negative energy effects in specific setups, like the Casimir effect between close plates. And Hawking radiation theoretically involves negative energy flowing into the black hole.
So quantum physics allows fleeting negative energy.
It seems so on microscopic scales, but then you run into quantum inequalities.
More rules?
Sort of. These are theoretical limits suggesting you can't have too much negative energy for too long in one place. You might get a brief burst, but it likely has to be balanced out by a bigger amount of positive energy nearby, like a cosmic energy loan with high interest.
And what does that mean for building a wormhole big enough for a person?
It means the amount of negative energy needed might be astronomical, perhaps concentrated into a region smaller than a proton, but with densities far beyond anything imaginable. Huge, maybe insurmountable hurdles for making macroscopic wormholes or warp drives stable.
So GR gives the blueprint, but quantum physics and energy conditions slam the door shut for now.
It looks that way, which leads physicists to explore even more exotic theoretical ideas within GR, like Gödel's rotating universe,
What's that?
a solution to Einstein's equations describing an infinite rotating universe that inherently contains closed, time-like curves, paths back into the past. But, well, our universe isn't infinite and rotating like that.
So mathematically interesting, but not our reality.
Right. Then there are things like cylinder time machines or Mallet's idea using circulating light. But these usually need infinite cylinders or run into energy problems or singularities points where the physics breaks down. Hawking even proved a theorem suggesting time machine creation in a finite region probably needs negative energy.
It seems like every loophole has a catch. What about cosmic strings? Want a time machine using those?
Cosmic strings are another wild theoretical idea, super dense, thin defects left over from the early universe. Got proposed using two infinitely long strings moving rapidly past each other. Their gravity could theoretically warp space-time enough to create time loops.
Infinite strings.
Yeah.
Sounds practical.
Yeah, exactly. We haven't seen cosmic strings, let alone infinite ones we can move at near light speed. So, again, theoretically intriguing, but physically seems way out there. Might still violate Hawking's theorem principles, too, due to the infinite nature.
So after this whole deep dive, what's the verdict? Are warp drives and time travel totally off the table?
Based on current science, the verdict is extremely unlikely. General relativity opens the theoretical door, yes, but the energy conditions, the need for exotic matter, the quantum inequality constraints, they all pile up to make practical realizations seem incredibly difficult, maybe impossible with known physics.
A bit of a reality check then.
It is. But, the book rightly points out the history of science is full of impossibles becoming possible.
Like heavier than air flight or lasers.
Exactly. Superconductivity, macroscopic quantum effects, things that seemed crazy once. Maybe a future theory, like a complete quantum theory of gravity, will change the picture entirely. We just don't know.
Is there maybe even a silver lining to it being so hard? The book hints at that.
Yeah, the idea that maybe the vast distances and difficulty of FTL travel are a blessing in disguise, preventing potentially messy encounters between civilizations. And on time travel paradoxes, if many worlds is right, you don't mess up your own past, you just create a new branch. If not, maybe the banana peel effect prevents paradoxes anyway.
It still feels like time travel opens a huge can of worms for causality.
It absolutely does. Even the possibility of building a time machine in the future raises deep questions about predicting the present. We really need that unified theory of quantum gravity to make real progress here.
Well, this has been completely fascinating, even if my hopes for a weekend trip to the Jurassic are dashed for now.
Yeah, probably for the best.
But seriously, digging into this stuff, even the seemingly impossible, really pushes our understanding of gravity, quantum mechanics, space, and time to the absolute limit.
It really does. These thought experiments are incredibly valuable for fundamental physics.
So, while that quick jaunt to Alpha Centauri might be off the cards, exploring these ideas keeps revealing how weird and wonderful the universe is. It makes you think, what other impossible things are we just beginning to glimpse?
That's the exciting question, isn't it?
Thank you so much for joining us on this incredibly mind-bending deep dive.
My pleasure. It's always fun to speculate on the edges of reality.